I promised you this, and we never got it last time. Let's see if it works today. Just because I think it's interesting. I'll cut it to mute, and I'll put the sound on later. So we've been talking about pipe flow, and we've made the point that we've made the point that pipe flow looks at this behavior between friction factor and Reynolds number. Friction factor is really a surrogate for an Euler number, a force, a pressure divided by rho v squared. And it's really not very much different from the behavior that we expect to see if you looked at flow instead of in a pipe, where you have this shear stress applied on the inside of the walls, which is the friction force which resists flow, to if you capped off the two ends of the pipe and you had air or water flowing past it and causing drag. And so when we talk about external flows, which is the topic that we'll talk about after we finish about pipe flows, it's really very similar. It's basically looking at flow equivalence through the Reynolds number. And then once you have the right flow regime, you look at equivalence, dynamic equivalence, and that dynamic equivalence, again, is a kind of Euler number. It is the Euler number, a much more straightforward Euler number than friction factors that we've used in pipe flow. So they're basically the same problem. It happens that one is inside a structure, the other, where our interest mainly is in how much power do we have to apply, or how much pressure do we have to apply to be able to make flow go in that pipe. And the other one is typically we have a structure and we have a given flow rate, which is happening anyway because we're driving the plane through the air, or the water tower is sitting in the wind, or the flag is sitting in the wind. What are the forces that are then applied on that structure as a function of the velocity of the fluid around it? And so this isn't a bad representation of that. You have this umbilical, which is sucking water out of the sea, I guess it's the sea, and squirting it out of the jet to allow these guys and gals to move. And you also have drag on these individuals as they go into the water. I imagine as they go into the water, they slow down because there's a force that's applied to them by the fact that they're killing momentum of the water. Water's static, they're moving, their momentum is being killed as they try and move through the water. And so it really is a kind of continuum behavior. So internal flows and external flows really aren't very different in many respects. So I think it's quite impressive. So just interesting. So for $125,000, if you have that to spare, if you've paid off your student loans already, and you don't want to buy that first fancy car with your first job, then get yourself one of these, and maybe you can make some money on the circuit. I don't know if they're making money on these videos. You can, when we put these YouTube videos up, by the way, you can monetize it, as they say. I've never actually done that. I said one year that we'd monetize it, we'd use it to go out and have a drink, but they're not monetized right now. And monetized means that just ads come up as you watch them, if you watch them. If you're here, perhaps you don't need to watch them. So I think this is kind of cool. Are we done yet? Close enough. Seen enough? Well, you can find it, I'm sure, if you need to find it. Hopefully it hasn't been too loud. I guess it hasn't been completely muted over me. So that's the deal. So let me close that off. I don't know what other things we had. I always said when we came into this that I thought that pipe flow wasn't very exciting, but of course some aspects of pipe flow, I guess, are kind of important. Deepwater Horizon was one of the issues where there was leakage around a pipe. That pipe happened to be buried a few thousand feet in the ground, but nonetheless, gas flow leaking from a bad seal on the outer concreting job on the lining ultimately caused a problem by allowing gas to come up to the rig and cause an explosion, which destroyed the rig and then which left the well open to a spill into the Gulf of Mexico. 4 years ago, was it now? Yeah, 2010. And the other interesting thing related to pipe flow, I think, is this picture of the gas pipelines, not the XL type, or the Keystone pipelines or XL pipelines that we talked about, which would come down through the central part of the U.S., through Nebraska's sand hills, which I actually drove across this summer, which are quite pretty, and down to the Gulf to refineries. But this is a network of natural gas pipelines, and it's actually amazing. You're all getting stuff up from the Gulf originally, up to the northeast where the consumption is. But also now you see this must be all Marcellus and Utica stuff in western Pennsylvania and Ohio. And this looks like, these look like trunk lines for gas to come out to supply into the trunk pipeline and be able to transport it elsewhere. And as I mentioned the other time, northern Pennsylvania, which I guess would be here. I can't quite see are the borders on here. Now this is West Virginia right here. So this is probably us right here, I'm guessing, right? Northwestern Pennsylvania is where these salt deposits are, where they make these caverns, which are storage sites for gas before they send it very quickly on a short distance to New York City for everyone to turn on their ovens at 6 o'clock in the morning before they begin their commute or whatever. So anyway, so actually pipe flow can be fun, I suppose. All right, what we'd been talking about before, if you remember, if I just zip back here, this is basically, this one page is really all we need to understand. And we made the case that we can divide calculations into 3 types artificially. We talked about the first one, which is type 1, which if anything turned up on your third midterm, it would only be that one. And it's relatively straightforward because if we have velocity prescribed and our geometry prescribed, we can calculate straight away our friction factors, because friction factors are typically a function of Reynolds number and geometry. And so we did one example calculation. For prescribed flow velocity, we could calculate what basically the head drop was before. And we also did a calculation for the jet lev to calculate what the power was needed to be able to have water going at a specific velocity to give lift. And so we've done those. And so the more complicated ones are when we want to be able to prescribe geometry and prescribe the pressure we apply across the system and figure out what the velocity is, because we don't initially know what the Reynolds number is. And so we'll do some problems related to that. And also the other one is where we want to actually dimension something, where we have some constraints, and we want to know how big the pipe has to be to carry a flow rate of a given magnitude. And so those are the other 2 components. We've talked ad nauseum about the energy equation set as Bernoulli. Just to remind you, upstream, downstream, pump head, positive if you're pumping, negative if it's a turbine and you're taking energy out of the system. This alpha we're not going to care about. We're going to set it equal to 1. And the head losses come in 2 flavors, either as major, which are small incrementally but large overall over long length, or minor losses where we assume typically that it's turbulent and therefore there's a single value friction factor that doesn't vary with Reynolds number. When we're looking at major losses, they can be laminar or turbulent. We know exactly what the relationship looks like in terms of these 3 regimes, which are split up on some number, 2,000 to 4,000. In the fully developed turbulent regime, they're a function of relative roughness. And so these are no longer a function of Reynolds number once you get beyond this threshold number. But at low velocities or low Reynolds numbers, less than 2,000, and we know that Reynolds number for this use is always defined as a function of characteristic length is a diameter or an equivalent hydraulic diameter, that for laminar flow it's some function of a constant divided by Reynolds number. And so we've spent some time talking about this. So this is what feeds into this. Okay, so that's the 5-second recap for the morning. We've seen that multiple times. Okay, so let's spend our time going through some examples, not doing them in excruciating detail, but talking maybe about the big picture. So they all revolve around this energy, so-called energy equation. Okay, so hopefully you're comfortable with that. And we'll do it in these 2 particular flow types, so-called type 2. Doesn't matter that we know the Roman numerals for these, where we want to define flow rate or where we want to define geometry. It's kind of artificial. The only important thing to realize is that the ones where velocities are prescribed are the easy ones to do, and the other ones are perhaps more involved. So, maybe we're doing type 1. I guess it is where a velocity, no, actually it's not. It's not really type 1, it's borderline between them. So this is a question. So there's a horizontal pipe which is supplying some fluid out of the page. There's a connection made to this which comes out through a valve, a faucet, and it goes through a T. The T has a little surge tower in it. So the reason for having the surge tower is that maybe if this is flowing and you close this, then all the water that's flowing down here has momentum v squared over 2g. And if you're shutting this, it stops abruptly. And so what it might want to do is to carry on, not by going this way, but by diverting up this way against an air cushion in the top of this. And so I don't know whether it's a common fitting in a pipe network, but it's certainly a common fitting in hydroelectric plants where you have a reservoir, penstock that feeds the turbine holes. When you shut the gates of the turbine holes, you don't want all that momentum knocking those gates off, just like we saw in the Russian television movie maybe 8 weeks ago. And so what you have is when you shut the gates, there's a surge tower, which is typically, if it's in a hillside, it's either outside the hillside or it's actually tunneled as a vertical shaft in the hillside. The water stops against the gate, and instead of everything stopping, the stuff upstream piles up and just raises the elevation in the surge tower, surge shaft. And sometimes that surge shaft is closed, and so there's an air cushion that develops with pressure, which kind of cushions the blow. Sometimes it might be open, which just allows it to come up to its natural height. Clearly it won't go higher than the water level, because that's, even with inviscid flow, that would be the maximum height, as we know from our other calculations. And so having a surge chamber is not an unusual thing in bigger plants. I don't know whether it's a big thing in this kind of construction. So I digress. So what's the question? The question is that originally there's water flowing in this, and the pressure initially, in the pipe, as we go in this the streamline direction, initially the pipe is at 400 kPa when it's closed. So this is 400 kPa. When that height of water, when that flow rate is in here, then the air in here, the height of this, the water level here is 0.4 meters. But it's stagnant flow. Actually, nothing's flowing at all. And since it's fed by this 400 kPa force pressure in this container, by definition, you could use Bernoulli on this. The velocity here is 0, the velocity here is 0, the elevation of these 2 points is 0, therefore the pressure drop along here has to be 0 as well. There can be no head losses, right? Because there's no velocity in the system. All of our head losses are a function of velocity. So the initial pressure all the way through the system is equal to 400 kPa. And so then we come and we open this valve. And we open this valve, and all of a sudden the pressure at this point is going to be now equal to atmospheric. This is still going to be 400 kPa, because that's what's prescribed. And so there'll be flow in the system. There'll be flow in the system which will readjust this limb of water in here, but it won't be flowing, right? It'll readjust as you change the pressure at this point, because now if the pressure here is 0 and the pressure here is 400, there's going to be some change in pressure along here that will be different along these two segments. These will be linear segments. They won't necessarily be a straight line, but the question is, what is this new pressure here at point 3? So at point 3, we don't know the pressure. Also, since we've just opened this up, at point 3, we don't know the velocity either, right? P1, we know the pressure. Here, we don't know the velocity either, right? Because we've just opened it. And so we have one unknown here. The elevations are the same. So if we just draw a straight line through here, we can have Z1 equals Z2 equals Z3. Unconventional way for us to write this, but that's clearly going to drop out. And so what we'd like to know, I suppose, is we'd like to be able to solve for the pressure at this point. This is the only, we're trying to solve for how much this cushion of air changes from the pressure originally being 400 kPa. So pressure 3 at time 0 is equal to 400 kPa. Pressure at point 3 at time nu, I guess, we don't know. If we know what that pressure is, we know the amount of mass of air that's been trapped in that system is the same, so the mass hasn't changed. And so if we know what the pressure is at this point here, we can perhaps try and figure out exactly how this height might have changed as a result of the pressure. It won't be directly equal to the pressure multiplied by the unit weight times the height of that fluid, because there's a pressure already acting in the system, so it's a bit more complicated. But we want to be able to figure out what this is. This is our first thing. So what do? We have two unknowns here, so we can't really solve that. We have one unknown here, so presumably we could solve for the velocity at point 1. First step. Bernoulli between points 1 and 2, bless you. So pressure at 1, velocity at 1, elevation at 1. Pressure at 2, velocity at 2, elevation at 2. So upstream, downstream. Elevations are going to drop out because they're the same. Pressure at point 2 is going to drop out because it's atmospheric. Velocity 2, we don't know. But if this is a large pipe, then, and it says large pipe in some case, does it? We're going to take this to make our life easy as 0 also. And so we have major losses in the pipe, which are these, which are acted on the average velocity in the pipe, not necessarily the fitting. It happens in this case that the fitting and the pipe diameters are the same, so they're the same velocities. And minor velocities due to flow in the T. Not because it's going up the T, but because it's going across the T, a branch T, and it's going across. So of these, the only things, we certainly know the pressure at 1, which is still 400 kPa. We have a friction factor in the pipe. And so if we write this in terms of the things we know, yeah, okay. So this is this friction factor here. This is length over diameter here. This is the loss coefficient for this. So this is just the loss coefficient from going through the T. And I'm trying to work out why. Oh yeah, okay, so it's a plus. So this term here is this. This term here is this. And it just so happens that these two velocities that we have, because the velocity in the fitting and the velocity in the pipe are the same, that we can combine these. This should just be 1 plus F over LD plus sum of KL times V squared over 2G. And so we know everything in here except for the velocity, and we can solve for the velocity. I won't go through the math to do that. So now we have a velocity at point 2. I wrote this as 1, but it's 2, isn't it? So we now have this, which is equal to 6.88 meters a second. So now we have a velocity here. We know from continuity, since there's no flow going up here, that V2A2 has to equal V3A3. And so if both of these areas are the same, then these magnitudes must also be the same, right? So the velocity at point 3 has to be the same. We've already kind of assumed that in the fact that we've calculated our flow through the pipe. And so now we can write, if we know what the velocity is at point 3, presumably, which is the same as velocity at 2, these two are the same, presumably we can write our expression between a couple of different places. We could choose either this point and this point, or we could choose this point and this point. Either one would give us exactly what we need because we know everything at the other point. There's only one unknown left, which is P3. We know everything here, and we know everything here. And so here they've chosen 1 and 3. So this is now between points 1 and 3. P1 we know is 400 kPa. V1 squared, we're taking the big pipe assumption. The elevations at 1 and 3 knock out. P3 we'd like to know. And V3 is the same as V2, which we know. Which is the same as this, which is 6.88 meters per second, as is this. And so if we rearrange this in terms of what we might want to know, what do we want to know? I guess we know P1, we'd like to know what P3 is. So we can rearrange it in terms of that. And this is this expression. So now what we're doing is we're taking the flow velocity in the at point 3, and we're putting it inside this. So this is that. This is the loss in the pipe. This is the loss in the fitting. So now the pipe originally was the full length of pipe from here to here. So originally the length over diameter, the length was equal to 8 plus 5 meters, which is 13. Now, since we're going from here to here, the length is going to be equal to 8, and the diameter is still equal to 0.02. And so this now should be equal to 8. This is equal to 0.02. The loss, well, the loss coefficient before was taken as 0.9. Just, you can go back to one of our tables. You could make the argument that the loss coefficient could be half of that because it's going through half of it, or that it's still equal to 0.9. I'm not sure. I would be inclined to use half of it, but here they've used the full amount, 9 in this case. And so we know everything within this portion here to be able to calculate the remaining part. We know the velocity in the fitting, through the fitting, which is the flow in the pipe. We know the pressure in the big pipe, which is 400 kPa, and the only unknown we have is this pressure here. And so we can solve for, this allows us to solve for P3. This before had allowed us to solve for V2, and then as a function of V2, it allows us to solve for V3. So that was the calculation. We solve for the output velocity, the velocity in the pipe, these two are the same. If we know what V3 is, then we could solve for this one. So now, what we have, if we go back to our picture, we knew originally what the pressure was within this fitting, which was 400 kPa. We now know what the new pressure is, which apparently, if you go through the math, is 187 kPa. And so I imagine if we drew this particular surge tower to scale, then this is point 3. This is some height, and this is pressure of the air in there. And so initially we had the pressure at point 3 was equal to this, and then it comes equal to this. What else do we know about the system? We know that the mass of air in here equals constant. And so no matter if this pressure changes, so presumably if the pressure at this point has changed, it's reduced, I'd imagine that the pressure at this point, which is the pressure that controls the pressure of the air in here, will also have reduced, right? Because it's a same column of air. If the pressure at the bottom reduces, the air would expand in the column if it's subjected to the same pressure. So what we can do then is this kind of complicated view at the bottom, but it's kind of drawn out here, is we know that the pressure at the bottom of the column has changed from 400 kPa to 187 kPa. We know that the mass of air within the surge chamber is the same. Mass of air is defined as the density multiplied by its volume. Its volume is going to be equal to 0.5 meters minus h0, which is this height here, multiplied by the area of the surge chamber, which has some diameter. It'll be the same in both, perhaps you don't need to calculate it. And so, and the density of the air multiplied by that has to be constant. So in other words, we have this expression here, which we could put into this. So we have the volume here, which is equal to the cross-sectional area, the height of the whole surge chamber, minus the height of the water column. This is the amount of air that's in the system. We know from the ideal gas law that pressure is equal to density, gas constant, and whatever the temperature is. And so we can divide both sides through by RT, and if we do that, we get density. And so if we substitute that into this expression here, then we end up with the mass being constant is equal to the density at when it's open, the valve is open, versus closed. So the density of the air when it's closed, the volume when it's closed, the density of the air when it's open, volume when it's open, both will be different, but they have to equal each other. And if we substitute in for the ideal gas law into this, we end up with this expression here. So what do we know in this particular case? We know the pressures in the column, kind of, because we know the magnitudes of the pressures at this particular point here. We know that the temperature is not changing, so we can get rid of that. We know that the gas is the same, so we can get rid of that. We know that in the initial case where the valve is closed, the height of the water column is 0.4, which is this. We don't know what the height of the column is once it's open because it's changed, and that's what we're trying to solve. And so now what we can do is we can try and figure out the magnitudes of the pressures which are acting in this water column. The pressure that's acting in this water column when it's closed is going to be the pressure at 3, and the pressure closed is going to be equal what? The pressure at 3 minus the unit weight of water times H0. So we know this pressure because we calculated it from Bernoulli equation, either when it's closed, when it's trivial, or when it's open. But we want to be able to calculate the pressure at the air cushion, so we just have to use the manometer equation. So the pressure at the air cushion when it's closed is equal to the pressure at 3 when it's closed minus the unit weight times H0. Go up, you reduce the pressure. And so that's exactly what this is. If we substitute this into here, then we have this defined in terms of a height we know and height we know. If we do the same for the case when it's open, the pressure open is equal to the pressure at the bottom when it's open minus the unit weight of the column, unit weight of the fluid times the height of the column, which we don't know. And we can substitute that into here. Lots of red lines going all over the place, I realize. And so now we have the left-hand side completely defined. We have this pressure has an unknown value of the height, has an unknown value of the height, but otherwise we know everything in this equation, and we can solve for the magnitude of H0. And it turns out to be 0.285 meters. So in other words, as you suspect, if this pressure reduces, then the air expands. If the air expands, then it drives this water column down. It still has the same mass in there. So Not a question I think you'd ever be asked on an exam you might like to know, but just one that exercises our thoughts. But the important things are to understand the process. The process is to figure out where you can write Bernoulli between, where you only have one unknown, and that's between points 1 and 2, which allows you to get the velocity through the system. Once you have the velocity through the system, de facto, you have only one unknown at this point. You can solve for the pressure 3 as a function of the different losses within the pipes, which we're adding in, which is different from where we've done this before. Once we know the pressure at point 3, when it's open and when it's closed, then we can go through some mental gymnastics to figure out exactly what happens in the surge tower to be able to do it, so long as we realize that the amount of air in the system is constant. In other words, we conserve mass. So, more complicated than we need to. Challenging problem, but maybe one that is interesting, and actually an example of a real-world problem. Not applied to pipe systems, but actually applied to surge chambers in dams, for instance. Yeah, sorry, shout.
So, in the first part, how did you assume that the average velocity was equal to velocity 2 and velocity 3?
Because, well, so you're not given any other information. So I'm assuming, I guess I am assuming, and they're assuming that you assume, since this is a question from the book, that the diameter out of this pipe is also the same as 0.02 meters. So that's an implicit assumption. It's not really stated in here. I don't think it is. Water level closed surge chamber is 0.4. Valve fully open. Pressure at point 1 remains 4. Okay. Determine the new level of water in the surge chamber. Assume the friction factor is 0.2. And it tells you what the fittings are. Yeah. So you have to assume in this case that this is equal to 0.2 meters. If this is a different diameter, then you could still do this calculation here, but you just have to know what the diameter was. So it's unstated here. But they've assumed it, and I've assumed it on their behalf. So that's the reason. Okay. Any others? All right. Okay. So type 1 apparently flow question. Not really, right? It's kind of type 2 because we had to determine what the velocity was. We didn't know what the velocity was to start with, so it's kind of a hybrid between a type 1 and type 2. In the first one, we knew what the velocity was. The velocity is 0. Trivial problem to solve for the internal pressure. In the second part of the problem, we open the valve and we don't know the velocity. So it really is maybe not just a type 1, but type 2 as well. All right, let's do something else. Pump coming out of a tank. The pump adds 25 kilowatts to the water, and it causes a flow rate of 0.04 meters cubed per second. So that's a volumetric flow rate. So this is Q is equal to 0.04 meters cubed a second. Determine the flow rate expected if the pump is removed from the system. Assume a friction factor. So in other words, I guess if we're assuming a friction factor, we know that if you look at our Moody chart, that we are here, right? We're in this region, since it's constant. So it's in the fully developed turbulent region. So it's often convenient for us to prescribe it as turbulent just because it makes it an easy problem to solve. In this particular case, we don't know the initial height of the tank. And so we know that it's flowing at some rate. So we know Q2, for instance. And Q2 has to equal the velocity at 2 multiplied by the area at 2. And so I suppose if we know this, and we know the area because we know the area is equal to pi d squared upon 4. And we know the nozzle diameter. So we know the area, and so therefore we know the velocity. And so if we write behavior here, we know the velocity. If it's atmospheric, we know the pressure, and we know elevation. Set it equal to 0, I suppose, that magnitude. What do we know here? Big tank assumption, atmospheric pressure, elevation, we don't know, but we know it's equal to h. So I suppose we have one unknown here. We have a known pressure, a known elevation, a known flow rate, and so we should be able to write between upstream, pressure, elevation, downstream, pressure, elevation, losses in the pipe, and pump in the head. So of these, we know that this is equal to 0. We know that this is equal to 0. We know that the elevation 1 we don't know. We know the elevation 2, if it's null, it's 0. We know that this velocity is 0 for all of our assumptions. But we have an elevation, we have a pump head that we have to include, and we have a velocity in the fitting, right? This is V2, and we have a velocity in the pipe. And in this particular case, the pipe is a different diameter, and so I guess V is not equal to V2. So we have to be aware of that. And so in this, we also know the value of the pump head. So what do we know? Pump head is equal to what? It's equal to the power. We've sometimes called it, I'll write it both ways, power divided by G times rho times Q. This, of course, is mass flow rate, m dot. And so the pump head is also, if you want to write it out the other way, is the power, which we've also written, this is the same. P is equal to W dot. It's just the shorthand we've used. It's also equal to gravity times the mass flow rate. These expressions are identical. Power, mass flow rate, gravity, power, mass flow rate, gravity. And so we know the mass flow rate, right? Mass flow rate is Q times density. And we know the flow rate is here. We know gravity, and we know this is 25 kilowatts. Okay? And so we know everything in HP. So we know HP, I guess, as well. And so what don't we know? I think the only thing we don't know, we know the velocity at point 2. We know the velocity in the pipe just by the ratios of the areas, because I guess we know that V2A2 is equal to VA. And so we can certainly link these two velocities by substituting. And so the only thing that we don't know is the height. And we can calculate that, and it turns out to be 133 meters. Okay? So the pump's turning, it's putting energy into the system, and now we turn the pump off. We have 132 meters of head in the system. What is the flow rate that happens with the system? Hold on a sec. Why is this? Well, no, this is the combined component. And so I guess this, yeah, all right. So the calculation here is the combined head within the tank and also the head that's put into the system by pumping, and that's 132. If we know what the head put in by pumping is from this expression here, which we do know, because we know the mass flow rate, because we know Q, and we know the power is 25 kilowatts, then by definition we know HP. If we know HP, then we know that subtracting off HP gives us the true head. So this is actually the head that's in the tank. So this is actually 63.8 meters. So we have that. And now we turn the pump off and we see what happens. And so now we can rewrite this expression between 2 points. We can write it again between the upstream point and the downstream point. And what do we know? We know so for the second part, if I make this slightly smaller, what do we know? Upstream, we know that H1 is equal to 69.5 meters. Where did I get? So, this is 69.5 meters. Big tank, atmospheric pressure, so we know everything upstream. So certainly we can write it upstream, we know everything. Downstream, what do we know? We know the head, this is Z. Z2 equals 0. It's coming out atmospheric. And we don't know velocity 2. So what we can do is we can write Bernoulli again. Most of the terms are going to drop out. If we write Bernoulli, I'm running out of space and I don't have anything to do it. But if we write it upstream, the only term upstream is going to be Z1. The only term downstream is going to be V2 squared over 2G. And it's going to be plus the head loss term, friction, length over diameter, and a different velocity, V squared over 2G. So if we write that here, this is the elevation upstream. All the other terms are 0. The pump term is also, by definition, equal to 0. We've turned it off. So this is the upstream portion only. The downstream portion has the velocity coming out of the nozzle. The velocity that defines the head losses in the pipe, the major losses, is not the same as that because they're different diameters. And so we just have to be cognizant of that. And so we can write this by using continuity to link these two together to give us a given velocity and solve for that velocity. It's probably easiest to be able to, doesn't matter. We're asked for the flow rate. So even if we calculate the velocity here, or the velocity in the pipe, we're just going to have to multiply by the respective appropriate area to be able to calculate what the flow rate is. So we have to do it in 2 steps anyway. So you can calculate here velocity 2, or you could write it in terms of the velocity in the pipe. It doesn't matter. You'd end up with the same result. It's just that when you calculate the flow rate, you'd have to multiply by the appropriate pipe diameter. That's it. That's it. So, okay. Is this scintillating? Are you still with me? Okay. All right. Alan?
How do you know that a pipe is pumping water out of the tank and not into it?
You don't. I guess if you calculated, in this case it has to be going out of the tank because you're putting energy into the system. So HP is positive. If it was a turbine, for instance, I guess if you calculate, yeah, right. So if you calculate H to be negative in this case, you'd know that
So we think that that's what can only be doing the tank.
well, yeah, it's pumping it downstream. Yeah, they don't. Yeah, from the diagram. I don't know if they give this diagram in the problem statement, but the fact that you have stuff squirting out of the hose, I guess, is a giveaway. So yeah, there are some cases. So I think not in these particular cases. The pump here, it means that you're putting energy into the system, and the fact that you're squirting fluid out of the system in that nozzle at point 2 that you see here, that this little cameo here is stuff going out, is you'd assume that it's coming out. If you're given a question where you're given a tank connected to another tank with a, is that the next one? No, it's not. If you're given 2 tanks that were connected, then you might not necessarily be able to tell directly. But I suppose if you had 2 different heads in the tank and you knew that you were pumping to fill a tank, then you'd have to be pumping, I suppose, into the one that was already higher because you're pumping against the system. So yeah, I'm not sure I have a golden bullet answer for that, but in this case, it's squirting out. So yeah, because you do have to know it to write which one is upstream and downstream. But if you write them up the wrong way around, then it would turn out that the pump head would be negative or positive. Right? That would be the key. Okay. Yeah, good question. All right, are we good for the last one? This is the same. Just quickly, because this is, so type 2 is the one that we just did. Type 3 is a bit more complicated again. So this is the case where you want to dimension the pipe to be able to carry a certain amount of flow. Actually the typical calculation that you might want to do. Don't end up with a pipe that you're being able to figure out what it is, but you want to know what the best pipe dimension would be. They're often a bit contrived because they say things like keep the width to height ratio of the duct the same. And this is one that's also contrived as well. But here's a question. So you want air to flow through a pipe. It's a duct. You want it to go through at 100 meters cubed per second of air. You want the pressure drop of not more than 40 millimeters of water, not air, per 50 meters of duct. So the length of duct is 50 meters. The diameter of the duct, which is the hydraulic diameter, well, we don't quite know. And so that makes it a difficult question to calculate the friction factor, because the friction factor is some function of Reynolds number, which is velocity, density, a length dimension, and viscosity. And it's also a function of some roughness. Except in this case, the other key term, smooth. Smooth means 0, right? So at least that makes it a bit easier for us. And the significance of 0 means that when we're looking at the Moody chart, we're always looking on this curve here. So that's the smooth curve. So what do we do? Well, we realize that we've been asked to this contrived thing that we always want this width to height ratio to be 3 to 1. So we want it 3 times wider than the height. That's just an artificial constraint. No particular reason, just a game here we're playing, I guess. And so we can write Bernoulli between upstream, downstream, no pump in the system, only major losses in the system. And so we have to start writing our behaviors in terms of these. The pressure drop across the system will be P1 minus P2 over the unit weight of water because of this. And so this term here combined is going to be 40 millimeters. I was going to do it metric, but this is 40 millimeters. 0.04 meters, right? 4 centimeters or 0.04 meters. And so we're going to know what P1 over gamma W is. We're going to know what this is. We know that if the duct, as we go downstream, doesn't vary in section, that V1 and V2 are going to be the same. And so we can get rid of these immediately. We know if it's horizontal that Z1 and Z2 both go out as well. And so basically we're left with an expression which is just P1 minus P2 over unit weight of air in this expression, right? This is unit weight of air, is equal to friction factor, length over equivalent diameter, hydraulic diameter, velocity squared in the duct over 2 times gravity. This is really important. This is the pressure drop that we're measuring relative to the pressure drop in a length in air. This is how it's defined in the problem as a function of water. So we just need to be able to swap them out. I guess, of course, you could multiply this by gamma air over gamma air, and you'd get the relationship. And so this is the expression that we're going to have to solve for. So what we'd like to do is, we know that Q is equal to a velocity times an area. We know that the area is going to be equal to what? Area is equal to B times H, and which is equal to 3H times H. So we're going to have to define everything in terms of the height. So we can define the area in terms of the height. If we define the area in terms of the height, we've got the velocity defined in terms of the height. And so that's what this is here. So the velocity is equal to 100 from 100 meters cubed per second divided by the cross-sectional area, 3h squared, which is this. We can define the hydraulic diameter as 4 times the area of the cross-section divided by the pipe. The area is 3h squared. The perimeter is this length plus this length plus this length plus this length. So it's just the L-shaped one is 3h plus h times 2. And so that's this. And from the rest of this expression, we have the pressure drop defined just as this, our Bernoulli's expression here. And so without excruciatingly going through the details, the idea is to be able to define everything in some term we know, and we can define everything in terms of h. So this is the pressure drop, which we know. We have a pressure drop of 40 millimeters of water, so we can calculate exactly what this would be in terms of the actual pressure drop, which is what this magnitude is. This is delta P rather than delta P over gamma W. And it's equal to a friction factor, which we don't yet know. It's equal to a length over diameter ratio. It's equal to a half density of air times velocity squared. And velocity is defined in terms of h. The hydraulic diameter is defined in terms of h. And so also the friction factor is defined in terms of h as well. Why is that? Why is that defined in terms of h? Sorry?
That's the result of the equation.
This one here. Okay. Yeah. Right. Okay. So this is what. Yeah. Okay. So just solving this gives you. Solving for this gives you this expression here. Yeah. Right. Thank you. So solving this gives you this term here. We know Reynolds number, which friction factor is also a function of, is a function of hydraulic diameter, equivalent velocity, and kinematic viscosity. So we have Reynolds number as a function of this. So we have two equations. Reynolds number and the friction factor both include a value of this. And so what we can do is we could choose a value of h and calculate what the friction factor is, or we could just choose a friction factor and we could calculate from that friction factor a value of h. So we assume friction factor, calculate h, use this h to calculate the Reynolds number, and then we see if for that initial friction factor we had, it corresponds to the value of Reynolds number. And so if we do that, a friction factor of 0.2 gives us a Reynolds number of 3.32 times 10 to the minus 6. So what is it? So friction factor of 0.02 gives 3.2 times 10 to the minus 6. So 3.3, that's this number here, I guess, right? And that's not right. So it doesn't give us the right Reynolds number. So we choose a different, based on that, we choose a different Reynolds number, friction factor. This one gives a different value of h, which allows us to calculate a new Reynolds number. So 0.096 gives us a Reynolds number of 3.84. So 0.96 gives us a Reynolds number of this. And we see if that matches up with the value we get in the component, and it doesn't. But if we change the magnitude of the Reynolds number, we're basically honing in on a number that doesn't change very much as we go across here. And so ultimately, if you the one number that's congruent between a friction factor and a Reynolds number that actually match up are these two numbers here. And these two numbers happen to correspond to a height of this. If we know the height, and we know that the width is 3 times the height, then we know the relative diameter of our pipe. And so it just makes the point that if we don't know the geometry of our system, we have to iterate to be able to do it. It's not all that straightforward to do. We have to make some assumptions and make a trial guess. As a function of that trial guess, we ultimately end up honing in between it. But but in any case, you need to be able to realize exactly what's going on. So this isn't very different from the very first example we did a couple of sessions ago when we looked at flow along a duct. We know that the velocity upstream and downstream doesn't change. We know the elevation upstream and downstream doesn't change. And so the Bernoulli equation works out to be a very straightforward expression, which we can then use to be able to figure out exactly what's going on. Okay. So a little involved in that case, but perhaps illustrates the fact that it's not so easy to do. But it's perfectly easy to realize based on this idea that you're trying to find a value of the friction factor and the Reynolds number, which also satisfy the geometry in the flow rate. Okay, sorry for going over, but we'll leave there. Okay, thanks very much.